The moon circles the Earth roughly once a month, but exactly how long does one orbit take? Newton answered with a single sweeping idea. The same gravity that pulls an apple to the ground reaches all the way out to the moon. In this video, we'll state Newton's universal law of gravitation, set it equal to the centripetal force the moon needs to stay in its circle, and solve for the period of the orbit. The number that falls out is close to 27 days, and hidden inside it is Kepler's third law. Newton's universal law of gravitation describes the pull between any two bodies. Gravity is a radial force. It always points along the straight line joining their centers. Its strength falls off as the inverse square of the distance between them, double the separation, and the pull drops to a quarter. Written as a vector, the force on the second body equals minus g times the product of the two masses divided by the distance squared, directed along the unit vector that points from the first body toward the second. That minus sign makes the force attractive, drawing the bodies together. The constant g, the universal gravitation constant, equals 6.67 times 10 to the minus 11 in Newton meters squared per kilogram squared. Two subtleties troubled Newton. First, why may we treat the Earth's entire mass as if it were packed into a single point at its center? Newton proved that any perfect sphere of uniform density pulls on an outside object exactly as though all its mass sat at the center. That proof is difficult. It waits in this chapter's appendix. So for now, we simply assume the Earth and the Moon are uniform spheres. Second, does the gravity between the Earth and the Moon form an action-reaction pair? When Newton first explained the Moon's motion in 1666, he had not yet framed his third law. Recognizing gravity as an action-reaction pair was the final missing key, and its absence delayed the Principia for years. Once complete, Newton's law was tested against the motion of the planets, and it succeeded spectacularly. For nearly 200 years, it matched observation almost perfectly. The first crack appeared only when astronomers confirmed a tiny stubborn drift in the orbit of Mercury in 1882, a wobble Newton's law could not quite account for. Predicting that drift became the very first triumph of Einstein's general theory of relativity, published in 1915. But for the Earth and the Moon, Newton's law is far more than accurate enough. Let's put it to work. Here is our problem. The Moon orbits the Earth in a nearly circular path. Picture the Earth on the left and the Moon on the right, separated by a distance r. Gravity pulls the Moon straight toward the Earth. That inward pull is the force arrow drawn from the Moon back toward the Earth. We know three numbers. The Moon's mass is 7.36 times 10 to the 22nd kilograms. The Earth's mass is 5.98 times 10 to the 24th kilograms. And the Earth to Moon distance is 3.82 times 10 to the 8th meters. From the previous video, the Moon's centripetal acceleration points inward with magnitude 4 pi squared r over t squared. Newton's second law in the radial direction sets the gravitational pull equal to the mass times the centripetal acceleration. On the left is gravity, minus g, times the Moon's mass times the Earth's mass over r squared. On the right is the Moon's mass times its inward acceleration, minus the Moon's mass times 4 pi squared r over t squared. The Moon's mass appears on both sides, so it cancels completely and the period will not depend on it at all. Rearranging, we isolate t squared as 4 pi squared r cubed over g times the Earth's mass. Taking the square root gives the period t equal to the square root of 4 pi squared r cubed divided by g times the Earth's mass. Now substitute the numbers. In the numerator, we cube the Earth to Moon distance, 3.82 times 10 to the 8th meters, and multiply by 4 pi squared. In the denominator, we multiply g, 6.67 times 10 to the minus 11, by the Earth's mass, 5.98 times 10 to the 24th. Evaluating the whole expression under the square root, the period of the moon's orbit comes out to 2.35 times 10 to the 6 seconds. 2.35 million seconds is hard to picture, so let's convert to days. 1 day equals 8.64 times 10 to the 4 seconds. Dividing the period by that, the moon's orbit takes 27.2 days. This is called the sidereal month, the time the moon takes to return to the same position against the background stars. But the month on your calendar isn't 27.2 days. The time from one full moon to the next, the synodic month, is longer, about 29.5 days. Why the gap? Because while the moon circles the Earth is itself sweeping around the sun. A full moon happens when the moon sits opposite the sun. By the time the moon has completed one full circle relative to the stars, the Earth has moved along its own orbit, so the sun now lies in a slightly different direction. The moon must swing through a small extra angle to line up opposite the sun again. That extra sweep is why the synodic month runs longer than the sidereal one. We can estimate that extra time. There are about 12 lunar months in a year, so during 1 month the direction to the sun shifts by roughly 1/12 of a full turn. The moon must sweep that much extra to swing back opposite the sun, and that takes about 1/12 of its period, the period divided by 12, which is roughly 2.3 days. Adding this to the sidereal months gives 27.2 plus 2.3, about 29.5 days. Right in line with the measured synodic months of 29.53 days. Now look again at our formula for the period and square both sides. The square root disappears, leaving the period squared equal to 4 pi squared r cubed, divided by g times the Earth's mass. Two things stand out. First, the moon's mass is nowhere in this result. It canceled earlier, so the period depends only on the size of the orbit and the mass of the Earth. Second, the square of the period is proportional to the cube of the distance. That is exactly Kepler's third law, which astronomers had drawn from observation decades before Newton, and here it falls straight out of the universal law of gravitation. That last step was the clincher. Kepler had run his third law from years of painstaking observation. Newton derived the very same law in a few lines from a single principle. For Newton, that agreement was overwhelming evidence that his universal law of gravitation truly governed the heavens, even though he freely admitted he could not say what gravity is or what causes it. One equation tied the fall of an apple to the swing of the moon and the march of the planets. That reach is why we still call the law universal. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.